Good day, everyone. I am Brando A. Pinheiro from Foundation University. I'm going to have a workshop presentation on Doppler effect of sound, learning with computer interactive simulation. Okay, so before I'm going to introduce to you the simulation, the computer interactive simulation that can be downloaded free. Okay, let me tell you first what is Doppler effect. When I say Doppler effect of sound, the Doppler effect of sound is the frequency shift or change of frequency when there is motion, relative motion of source of sound and the listener or both relative to the medium of sound. So the sound and the listener frequencies f of s as the frequency of the sound wave from the source when both the source and the listener are at rest, and f of o as the observed frequency when there is Doppler effect are related by the source and the listener velocities, v of s as the velocity of the source, v of o as the velocity of the observer relative to the medium and to the speed of sound wave, and that is v. Okay, so I have demonstration on this one. Okay, I'm going to demonstrate to you the Doppler effect of sound. Doppler effect of sound is the effect when there is relative motion between the source of the sound wave and the observer. Alright, so I have here the speaker. I'm going to play a pure tone sound whose frequency is 400 Hz. So this is how it looks like when the speaker is stationary relative to you. Now I'm going to swing this speaker around. I tied it with the rope, and you listen how the sound looks like when the speaker moves towards you, as it moves towards you, and how the sound looks like when the speaker moves away from you. Alright, so I'm going to play the pure tone song with 400 Hz, and I'm going to swing this around. Alright, as what you observe, as the speaker moves towards you, there is increase of pitch or frequency of the sound. And as the speaker flies away from you, move away from you, there is decrease of pitch or frequency of the sound. And that is the Doppler effect of sound. The computer interactive simulation on Doppler effect can be downloaded in this link. So just copy this link, open in any web browser, and download um, the computer simulation. This computer simulation on Doppler effect or the Doppler effect model was created using the Easy Java Simulations or EJS modeling tool, and it is distributed as ready to run compiled Java archive. So the requirements to run this simulation, if you have Windows, Macintosh, or Mac OS and Linux, so at least you must have, for all this operating system, you must have Java. Okay, so you cannot run the simulation if you don't have your operating system that doesn't have Java. This is how the computer simulation looks like. Okay, so this in this simulation you can explore the change in the wave that is produced by source or the observer motion, and you can even view what the situation looks like from the perspective of the medium, the standard reference frame, the source or the observer. So by clicking this one, so you can have reference frame of the medium, reference frame of the observer, the reference frame of the source. So this dot here represents the source of the wave, and this small rectangle represents the observer. Now you can change the position of the source by sliding this one. So going to the left is negative position, going to the right is positive position. For observer's position, you can also change by sliding this. Going to the left is negative position, going to the right is positive position. And then to change the source velocity, you can slide this. Towards left means negative velocity, towards right means uh, positive velocity. And the observer's velocity by sliding this towards left is negative velocity, towards right is positive velocity. So this is how the Doppler effect simulation looks like. So what will be the observed wavelength and frequency of the observer when the observer is at rest and the source is moving? It depends. So the observed wavelength is shorter than the wavelength observed by the observer when there is no relative motion between the source of the wave and the observer. It's shorter when the source is moving towards stationary observer. Okay, and that makes the frequency higher since the velocity there is no relative velocity wave. Okay, so it makes the frequency higher. The observed frequency will be higher. Now if the source is moving away from stationary observer, the observed wavelength will be longer, and that makes the frequency lower since there is no relative speed of the sound wave. So let us use the Doppler effect simulation to show what will be the observed wavelength by this observer if the source is moving towards the stationary observer. The observer velocity here is 0 and the source velocity must be towards right direction or positive direction. So we have the positive source velocity. So this is how the wavelength looks like. The wavelength of the sound wave is the distance between the two crests, okay, two consecutive crests. So this is how it looks like. So it's shorter than the wavelength when that these two uh, the source and the observer are at rest. So the observed wavelength here is shorter. So if I let the source move faster, the shorter the wavelength observed by the observer. All right. Now next is the source will move away from the stationary observer. So observer velocity here is 0 and the source velocity must be towards left direction or away from the stationary observer. So this is how it looks like from the observer. All right. So it is longer. The observed wavelength is longer than the wavelength when there is no relative motion between the source and the observer. This time the observer is moving and the source is stationary. Now the observed wavelength is the same when either the observer is moving towards the stationary source or the observer is moving away from a stationary source. The same as when there is no relative motion between the source and the observer. Still wavelength. But how come there is still shift of frequency when the wavelength is the same? That is due to the relative velocity of the sound wave. When the observer is moving towards the stationary source, the observed speed of the observer, the observed speed of the sound wave by the observer will be faster. And that makes the frequency observed frequency higher. Now, if the observer is moving away from the stationary source, then the observed wave velocity will be slower, right? And that makes the frequency uh, lower, the observed frequency lower. So let us use this Doppler effect simulation to see how it looks, how the wavelength looks like from the perspective of the observer, moving observer. So I set here the source velocity equals 0 and the observer velocity is towards right or positive. So this is how it looks like from the perspective of the moving observer. So the observer now is moving away, but there is no shift of wavelength. The wavelength is the same. So let us use this the Doppler effect simulation to see what it looks like if what the wavelength looks like from the perspective of the observer if the observer is moving towards the stationary source. So I set here source velocity is 0 since it's stationary, and then observer velocity is towards left, towards the source. So this is how it looks like. You can see the observer is now moving towards the stationary source. There is no change of wavelength. The wavelength is the same as when there is no relative motion between the source and the observer. Now, in general case, it is when the observer and the source are moving. It's either they're moving towards each other, moving away from each other, or they are moving at the same direction. So this is the equation for the observed frequency when these two are moving. Okay, the observer and the source are both moving. So the at numerator we have v plus v of o if the observer is moving towards the source, and then v minus v of o if the observer is moving away from the source, and v plus v of s if the source is moving away from the observer, and v minus v of s in the denominator if the source is moving towards the observer. So how it looks like using the Doppler effect simulation. This is how it looks like when the observer and the source are moving towards each other. So how it looks like from the perspective of the observer if the source and the observer are moving away from each other. So this is how it looks like. And this is how it looks like when the source and the observer are moving on the same direction. The source is moving away from the observer is moving towards the source, and the observed wavelength is longer, and that makes the frequency lower. And this is how it looks like using the Doppler effect simulation if the observer is moving away from the source and the source is moving towards the observer. And that's all for my workshop presentation. Thank you very much for listening. Hope you learned a lot from this workshop presentation.